In this last lesson, we discussed the topic of sequences of random variables. In the same way as we can be interested in the limit of a sequence of real numbers, we can be interested in the behavior of a sequence of random variables. For example, we can ask ourselves, what happens when we repeat again and again a random experiment? Then, if a random variable follows a probability law for a relatively small number of experiments, then the same variable follows the same law for a big number of experiments? Or again, is there a sort of universal law, a universal probability distribution, which can approximate all the other distributions when the number of experiments tends to infinity? All these are very interesting questions, and in this lesson we're going to provide an answer. To this aim, the first thing to do is to introduce a notion of convergence that is appropriate for random variables. This is called an almost sure convergence, and it's defined like this. Consider a sequence of random variables that is denoted with this symbol here, and consider also a random variable x that doesn't depend on n. With this notation, we indicate the fact that when the number n of random experiments tends to infinity, then the probability that xn behaves like x is 1, that is, it is certain. If this happens, we say that the sequence of random variables xn converges almost surely to the random variable x. A more compact way to express this is by using this notation here, where you can see AS that of course stands for almost surely. Recall that random variables are functions from the sample space of a random experiment to the set of real numbers. So we could have defined the convergence of the sequence xn as the convergence of a sequence of functions, which is a standard concept of calculus. However, that kind of definition wouldn't have grasped the probabilistic nature of random variables. This is why it makes total sense to introduce the probability function in this definition, because in the end, this is what we are interested in. In the following subsections, we're going to state and discuss the two most important theorems regarding the almost sure convergence of random variables. The first important theorem that we discuss is called the strong law of large numbers. It has been established by the great Russian mathematician Kolmogorov in 1929, and it deals with the concept of sample mean or empirical mean of a sequence xn of random variables, which is nothing but the arithmetic average of the first n random variables. The symbol is this one here, where the bar denotes the average and n denotes the point at which we stop computing it. With this in mind, let's see what the strong law of large numbers says. Consider a sequence xn of random variables, and suppose that they are independent and identically distributed. Recall that being identically distributed doesn't mean that these random variables are identical, but simply that they have the same probabilistic distribution. Recall also that independent means that the values taken by one random variable don't affect at all the values taken by the other random variables. It is very common to indicate with IID a set of independent and identically distributed random variables. There is a second assumption for the theorem to be valid, that is, all the random variables must have the same expectation value, mu, which must be a finite number. So to resume, given a sequence of independent and identically distributed random variables with same finite expectation value, we have that the sequence of their sample means converges almost surely to mu. So what the theorem is saying is that there is 100% probability that when n tends to infinity, the arithmetic average of the random variables tends to the constant random variable mu, which is the random variable that gives back always the finite number mu when evaluated in the outcomes of the sample space. This may all seem very abstract, but we are going to see immediately that the law of large numbers allows us to deal with very concrete stuff. It turns out that we can use the law of large numbers to establish if a die is fair or not. As we have said many times during this course, a single roll of a fair die produces one number between 1 and 6 with equal probability given by 1 over 6. As a consequence, the average of the rolls will be 3.5. Now, importantly, notice that the rollings of a six-sided fair die can be considered as a sequence of independent and identically distributed random variables with the same finite expectation value. So, by the law of large numbers, if a fair die is rolled a very large number of times, the sample mean, that is the average of the values obtained, must approach 3.5 with increasing precision. And in fact, this is exactly what it is observed. In this picture, you can see the theoretical mean at 3.5, and in green, the observed averages as a function of number of trials. As you see, at the beginning, we have quite a big discrepancy, but as soon as we reach 600 trials, the observed and the theoretical mean have almost the same shape, which of course leads to the conclusion that the die that we are using is fair. The second important result that we discuss is the so-called central limit theorem. To introduce it, let me remark that the strong law of large numbers says that the sample mean tends to the common expectation value of each random variable when the number of trials tends to infinity. However, the law of large numbers says absolutely anything about what kind of law is followed by the limit of the sample mean. This missing information is provided by the central limit theorem. Consider a sequence of independent and identically distributed random variables xn. Suppose also that all the random variables xn have the same expectation value mu and finite variance sigma. Then the standardized sample mean, that is x bar n minus mu divided by sigma, converges to a random variable which has a standard normal distribution. Every probabilistic computation performed over the standardized sample mean of identically distributed and independent random variables can be approximated for a sufficiently large number of samples by the same probabilistic computation performed on the standard normal law. The advantage being that dealing with the standard normal law in general is much easier than dealing with other distributions. A little bit of history. The first proof of this theorem in the case of a Bernoulli distribution of parameter p equal to half was given by Demoivre in 1738, and Laplace generalized this result in 1809. Instead, the proof of the modern version is the result of the multiple effort of the mathematicians that you see quoted here. And as you can see from these dates, it arrived more than 100 years later than Laplace. Instead, the reason for the name, central limit theorem, is due to the fact that in 1920, The Hungarian mathematician Georg Polya published a paper in which he said that this theorem was central in probability theory. There is an exception: the French school of probability interprets the word central in the sense that it describes the behavior of the center of the Gaussian distribution as opposed to its tails. A very nice example of a sequence of random variables that fulfill the hypothesis of the central limit theorem is given by binomial variables. Probably the best visualization of the central limit theorem is given by the so-called Galton board, also called beam machine, which has been introduced by the British mathematician Francis Galton. You can see the Galton board in this picture. Little balls or beans are dropped from the top, and they bounce either left or right as they hit the pins. And this is the reason why we can consider these bounces binomial random variables. When the balls are collected into bins at the bottom, we see that the height of the balls columns always approximate the bell curve of a standard normal distribution. We can understand why the balls tend to accumulate at the center by overlaying onto the pins the Pascal-Tartaglia triangle, which, as you may recall, contains the binomial coefficients. By zooming, we can see that there are many more paths leading to the central positions than those leading to the extremities. And when the number of balls is big, we see appearing the typical bell shape of the normal distribution.
The course of probability ends here. I hope that you have enjoyed it and you have learned a lot of things. However, keep in mind that we have just started to scratch the surface of probability. The next natural step is to progress in the study of probability and to apply it to statistics, which is the science of data processing. Statistics is grounded on probability, and the most important message that I want to pass here is that it must always be analyzed in the correct context. Without this, statistics can lead to very misleading interpretations. As an example of misuse of statistics, I will discuss the very famous Simpson's paradox. Consider this data regarding the number and percentage of students who graduated from high school 1 and 2. Let's start comparing the results of students in the two high schools using the total number of students who graduated irrespectively of their gender. We can see that 37% of students graduated from high school 1 and 40% of students graduated from high school 2. If we had just this kind of data at disposal, we would say that students in high school 2 are better than students in high school 1. However, let's see what happens if we compare the results of male students from high school 1 and 2. We have that 32.5% of male students graduated from high school 1 and only 28% graduated from high school 2. So it seems that male students in high school 1 perform better than male students in high school 2. At this point, we are naturally led to think that female students in high school 2 have performed much better than female students in high school 1. We're going to see that this is not the case. In fact, 52% of females graduated from high school 2, but 55% of females graduated from high school 1. So you see that both males and females of high school 1 seem to perform better than those in high school 2. However, if we consider the total number of them, we have an opposite result. This is clearly an apparent paradox that was discussed by Simpson and nowadays goes under the name Simpson's paradox. The solution of this paradox is far from being simple, and in order to understand it, one must study the complex and very fascinating methods that statisticians have developed. With this very brief mention of statistics, the course has really come to an end.